Hi everyone, myself Arun Raja, working in the Department of Aeronautical Engineering as Assistant Professor in Hindustan College of Engineering and Technology. In this video, we are going to see about the introduction to finite element analysis. First, we are going to see about the history of FEA. By the early 70s, FEA was limited to expensive mainframe computers. It's generally owned by aeronautics, automotive, defense, and nuclear industries. Since the rapid decline in the cost of computers and the phenomenal increase in computer power, FEA has been developed to an incredible precision. The accuracy of the FEA is mind boggling. FEA applications are developed in and around the globe. They are used to evaluate stress, temperature distribution in the mechanical components, deflection analysis in structural members, analyze the kinematics and dynamic response of the machines, perform variable vibration analysis. The basic steps of the finite element methods. First is providing a differential equation of the problem which is converted into an integral form. We are following two different techniques to achieve this. One is variational technique and then next is weight residual technique. The second step is to obtain a domain of the problem in which it is divided into number of parts called elements. Then division of the domain into elements is said to be a mesh. Then the third step is forming a typical element and a suitable approximation chosen for the primary variable of the problem using different interpolation functions, that is called as shape functions, and the unknown variables of primary variable at some pre-selected points called nodes. The additional nodes are placed either on the boundaries or in the interior of the values what we have given. The value of the primary variable at the nodes are called degree of freedom. Generally, the degree of freedom is maximized to 6. Then the fourth step, the approximation of the primary variable is substituted in integral form of we suggested in the first two equations. If the integral form is of variational type, it is minimized to get an algebraic equation for different unknown nodal values of primary variable. If the integral form is of the weighted residual type, is set to 0 to obtain the algebraic equation. In each case, the algebraic equations are obtained element wise and then they are assembled over the elements to get the algebraic equation for the whole domain, which is said to be the global equation. When we are obtaining the equation element wise is called elemental equations. Then the last step is post processing, in which the solution is done and the secondary variables of the problem are calculated from the solution. Then the nodal values of the primary and secondary variables are used to construct the graphical representation, either in 2D or 3D contours. In some cases of 1D problems, we can obtain a graph in 2D or 3D contours. These are the different types of finite elements which we consider for the problem. The 1D elements are called beam elements. They are two noded or three noded elements. They are one dimensional elements. When we are taking the 2D elements, the 2D elements have some length and thickness. In case of triangles, it is 3 noded as well as 6 noded. In case of quadrilaterals, we can get a 4 noded as well as 8 noded element. While considering the 3D elements, we have tetrahedrons, which contains 4 noded as well as 10 noded elements, and hexahedrons 8 noded to 20 noded elements, and the pentahedrons which constitutes 6 noded as well as 15 noded elements. Preprocessing of FEA is our way of communicating geometry to the solver. The accuracy of the solution is primarily dependent on the quality of mesh. How good your mesh, you'll get the quality of result. In simple words, we can say the person who owns the mesh gets proper solution. The better the mesh looks, the more accurate solution we get. A good looking mesh should have well shaped elements, and the transition between the density should be smooth with gradual skinny distorted elements. The preprocessing elements are supported by most finite element codes like 2D linear, 3 node quadratic, 4 node cubic. While the triangular elements are having 3 nodes, 6 nodes and 10 nodes, they are considered as linear, quadratic and cubic respectively, or else we can say this as 1D, 2D and 3D. In the tetrahedral elements, likewise the triangular element 4, 10 and 20. In considering the beam elements, the beam elements typically fall into two categories. One is to transmit the moments or not able to transmit the moments. That is the simplest way of considering a beam element. Then we'll move into the plate and shell modeling. The plate and shell are used interchangeably and refer to surface-like elements. These are not exact elements, they are surface-like elements used to represent thin-walled structures. We are representing these thin-walled structure by means of linear triangle, linear quadrilateral, either by parabolic quadrilateral or parabolic triangle. Then we will move into the solid element modeling. In tetrahedral mesh, the only general accepted means to fill a volume by using auto mesh. By using many FEA codes, we can generate these 10 noded quadrilateral, quadratic or 4 node tetrahedral element. The purpose of filling this volume is to generate more number of nodes, more number of elements to get more accurate result. The next is applying of boundary conditions, loads, constraints. Then the analysis is going to be linear static or dynamic analysis. Loads are used to represent input to the system in the form of forces, pressure, moment, temperature or acceleration. The constraints which we are using here is reactions applied to the loads, and these kind of constraints can resist translational or rotational deformation induced by the applied loads. Then considering the analysis of the system, boundary conditions are resumed constant from application to final deformation of the system, and all loads are applied gradually to their full magnitude. In case of dynamic analysis, the linear static analysis conditions will be changing with respect to time. Nonlinear analysis. The orientation and distribution of the boundary condition vary as displacement of the structure is calculated. When we consider the degree of freedom, the spatial degree of freedom refer to 3 translational and 3 rotational modes of displacement that are possible for any part in the 3D space. A constraint scheme must remove all 6 degrees of freedom for the analysis to run. Elemental DOF refer to ability of each element to transmit or react to a load. The boundary condition cannot load or constrain a DOF which is not supported by the element to which it is applied. A solid phase should always have at least 3 points in contact with the rest of the structure. A solid element should never be constrained by less than 3 points, or the only translation degree of freedom must be fixed. Then we'll move into the accuracy. The choice of boundary condition has a direct impact on the overall accuracy of the model. When we consider the boundary conditions, in structural members, we consider three different supports. One is fixed support, the second one is pin support or hinged support, and the third one is roller support. The constraints of different support conditions will be given in the picture. We'll look into this different translational and rotational motions provided by the support. Summary of pre-processing. In this completion of the above said methods, we'll just build the geometry and make the finite element mesh, add boundary conditions, loads and constraints, provide properties of the material, specify the analysis type like static, dynamic, linear or nonlinear plane stress requirements, and these activities are called as finite element model. Once the above said methods are completed, say for example the mesh is complete, the property and boundary conditions have been applied and it is the time to solve the model. In most cases, this will be the point where you can take a deep breath and push the button and relax while the computer is doing the rest of the work. Multiple load constraints and multiple inputs will be given at this time, and the final check will be done with respect to the model. This is what we are going to do with the post processing. We can see animated displacements, displacement plots, stress plots, and different specific results based on the inputs what we are giving into the system. If the process is not yet completed, then we have to review either the boundary conditions or loading magnitudes or the units what we have given to the system. Then the quality of mesh or the density of mesh which we done with the system. This is the FEA flowchart what we are discussed till now. Simplify the part by means of equations, assign the materials to the equations, apply load and different constraints, generate the mesh, review the mesh once again. If there is any possibility of providing a proper mesh, do it now. Then generate the solver and give the inputs to the solver, then solve. Then we are getting an output at the post processing results. Next, we are getting into the advantages of finite element method over other numerical methods. The method can be used for any irregular shape domain and of all bodies and all boundary conditions. Domain consisting of more than one material can be easily analyzed, and accuracy of the solution can be improved either by proper refinement of the mesh or by choosing approximation of higher degree polynomials. The algebraic equations can be easily generated and solved on the computer. In fact, the general purpose code can be developed for the analysis of large scale problems in different industries. That's it for the video. Thank you. Thank you very much.